Hey everyone, this is lecture number 7, review. I'm Kimberly.
And I'm Aparna. What we're going to go over is a recap on the previous lecture, which was wavelengths. We're also going to talk about the electromagnetic spectrum, Rydberg's formula, Einstein and electromagnetic energy, Planck and his theory on electromagnetic energy, and finally the Bohr model.
For our recap on the previous lecture with wavelengths, we learned that waves can be transverse or longitudinal. Generating a wave costs a lot of energy. Waves also transport energy, and the larger the amplitude, the larger the energy is. Waves can interfere, which can lead to unexpected minima and maxima.
We also learned about the wavelength formula, and wavelength is depicted by the Greek letter lambda, and it is equal to the speed, which is represented by v, divided by the frequency, represented by f. This formula is helpful when we determine the distance between two consecutive points on a wave.
Electromagnetic radiation is any form of radiant energy in the electromagnetic spectrum. Electromagnetic spectrum is a continuous range of radiant energy that includes gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, and radio waves. Sir James Clerk Maxwell found the electric field and magnetic field are perpendicular to one another.
Robert Bunsen developed the Bunsen burner to make light, and he found that with a hydrogen atom, light is emitted while burning it. Bunsen found the missing lights, and he found that hydrogen can emit those lights. He investigated how light could trigger chemical reactions involving hydrogen gas.
The Rydberg formula is used to calculate the wavelengths of light emitted or absorbed by a hydrogen atom. The constant is represented by R, which is 10,973,731.6 m to the negative 1. Lambda represents the wavelength, N1 and N2 represent the electron's energy levels. N1 is a lower energy level, while N2 is a higher energy level. He also has another formula which represents the wave number. Wave number is reciprocal of the wavelength.
Going on to Einstein's theory of particle-like properties of electromagnetic energy, we learned that Albert Einstein discovered the photoelectric effect, which is when high-energy radiation on clean metal surface with light causes the electrons to be ejected from the metal. He explained that the effect of the high-energy radiation was a stream of particles known as photons. This discovery helped to establish wave-particle duality, where light can behave as both a wave and a particle depending on the situation.
Planck's equation represents the relationship between the energy of photons and its frequency. He introduces the idea that energy is not continuous, but it is in units of quanta. Quantum is the amount of energy corresponding to one photon of light. Planck's constant, symbolizes H, is 6.626 times 10 to the negative 34 joules per second. The formula E equals hv represents V as the frequency of radiation and H as the Planck constant. This formula calculates the energy of a photon.
We learned that the Bohr model was the first successful model of the atom, and in this model, the electron of the hydrogen atom revolves around the nucleus by orbiting. Each orbit represents a new allowed energy level.
The transitions between orbits either emit or absorb photons. Electron transitions will occur when an electron moves between any two energy levels. Thus, this process is when an electron within an atom moves from one energy level to another, either by absorbing or emitting electromagnetic radiation, which can also be known as jumping between different orbitals within the atom, resulting in a change in the electron's energy level.
Thank you so much for listening, and we hope this clarified Lecture 7.